Great. Thank you, Lorenzo. And I'd like to echo the previous speakers that I'm really, really sad I can't be there. And I would love to catch up again, but unfortunately, I was not allowed to go. So next time. And I would like to thank the organizers for putting together a great conference. And also for allowing me to speak about our paper that I wrote with Yasminda Sidhu, Yingkai Ouyang, and Earl Campbell. And I have to say right off the bat that it was Yasminda and Yingkai who conceived of this project and did all the heavy lifting. And so the vast majority of the credit goes out to them. And so what am I going to talk about today? I first will talk about some of the quantum mechanical limits to the estimation of a single parameter. So the nature of the paper I'm presenting is extremely technical. So I've opted to not so much go through the details of the algorithms that we present in the paper, but rather provide the context for our results and then and give some examples. So we have in metrology limits to the estimation of a single parameter, but we never really measure just a single parameter. There's always multiple parameters lurking in around, and so if we start thinking about limits to the estimation of parameters, then by implication, we have optimal measurements. And now, if we introduce multiple parameters, then we have multiple optimal measurements. And then the question arises whether we can actually perform these measurements simultaneously, because we know very well that in quantum mechanics, that is not always possible. And so this leads to a Holevo version of the Kramer-Rao bound. And our paper is concerned with finding algorithms to achieve that bound. So, and then I'll finish my talk with an example from magnetometry. And that would be the argument why we actually care about this Holevo Kramer-Rao bound. Right. So to start with, I want to give a little bit of background for those of you who are not so familiar or semi-familiar with quantum metrology. So we can think of a measurement as a three-part process in a very general sense. We can create the circumstances for our experiments where we prepare a particular system that we then let evolve in a very controlled way. The only thing that we don't know is the parameter theta that gets imparted on our quantum state due to this evolution. And then what we do is we make some kind of measurement, and that gives us, of course, a probability distribution over our measurement outcomes, and that's our experiment. Now, in reality, there's often a feedback component, and I'm going to ignore this. However, this can also be incorporated in the formalism, but I'm not going to touch on that here. So so a physical intuition would be if I have a probability distribution, let's say of three possibilities, red, green, and blue, then all my probability distributions lie somewhere in this probability simplex, this triangle where my probabilities add up to 1. And if I let my system evolve according to some kind of parameter theta, then if I want to be able to measure theta and estimate how big theta is, then the probability distribution of my outcomes better move, because if it doesn't move, I will not get any information from my measurements. So what we can then do mathematically is define some kind of distance along the path theta and ask the question, how often do I need to take a measurement in order to distinguish between my two probability distributions, P and Q? And so we have to see this little line here connecting P and Q, and there are little ovals that are like regions of uncertainty within which we cannot sort of distinguish that these are indeed two different probability distributions. Right? So if we take this further, we want to define some quantity called the Fisher information that tells us something about how much information we gain in a measurement. So to first create a distance measure in our simplex, we can derive the following formula, which you see is a little bit almost like the normal Euclidean geometry, except that the terms on the right-hand side are being divided by p. And the effect of that is that if any probability p goes to 0, then your distance goes to infinity, diverges, I should say. And that means that this triangle that I drew here is when you talk about it in terms of the statistical information, is not a flat space, but it's highly curved, particularly when we get towards the edges. And so there's some interesting maths there, but a really interesting thing is that we have now a threshold for distinguishing two probability distributions, and that's when the distance delta s squared times the number of times we sample, if that is greater than 1, then we can call the two probability distributions distinguishable. And then we can continue and define the Fisher information as in some sense the speed, or the speed squared, along this curve from P to Q, or from Q to P. And so there's a lot of interesting maths here to do with curved spacetime. But for our purposes, this information, this Fisher information, is the average amount of information that we get out of a single measurement about our parameter theta. And as a consequence, this can be used to bound the precision with which we can measure theta. So that's the idea. All right, so then we have the Fisher information, but also a so-called quantum Fisher information. And so the difference between them is as follows. So what I've said so far really pertains to the Fisher information, or the classical Fisher information, where we have a probability distribution from the measurement procedure. So we've made a measurement. And then the Fisher information is a direct calculation that you do on the probability distribution. However, when we talk about the quantum Fisher information, we stop short of doing the final measurement and ask, okay, what is the best possible measurement that we can do? Because for the classical Fisher information, we've already committed to a particular measurement, and that may not be the best one. So the quantum Fisher information is the amount of information when you do the best possible measurement. And the really nice thing about this is that it becomes a property of the state, of the quantum state rho. And so then we can calculate the quantum Fisher information for our output state rho of theta once it's been our parameter theta has been imparted, and that's the Fisher information. So there is an optimization procedure there implicit, but fortunately we don't actually have to do the optimization in many cases, and this will become different when I talk about the Halevo Kramer bound. All right, so before I continue with the background, I want to sort of do a little plug for two things simultaneously. So I took a lot of the background material from our review paper that I wrote with Jaswinder for this new journal, Quantum Science, that is published by the American Institute of Physics. So it's new. I'm an editor. If you're interested in publishing in this journal, it's open source, then please drop me an email. All right, so, but also if you want to know more of the background of parameter estimation in quantum mechanics, then this is a review that you may want to consider. All right, so now we have the quantum Fisher information, and it is a property of the quantum state. And in particular, it is defined as follows. It is the expectation value, actually, of this operator L sub theta squared. And L sub theta squared, that is the so-called symmetric logarithmic derivative, or SLD for short. And it is typically defined implicitly using this equation here. And so that's unfortunate because, well, it makes it not an easy plug-and-play formula. But of course, people have been studying this quite hard. So many different ways of calculating L, theta are available. And so we can calculate the quantum Fisher information in many different situations. Particularly for pure states, it's a very straightforward procedure. And once we have the quantum Fisher information, we can bound the variance on theta, or the mean square error, by this inequality. And so n here is the number of times that we repeat the experiment, and IQ is the quantum Fisher information, which is the average information that we get in the optimal measurement. So here we have not defined what the optimal measurement is. We've just found a way to get a lower bound on the mean square error. Right. So and it's the SLD that actually determines what the optimal measurement is. In fact, if you look at the eigenstates of the SLD, that should be the basis for your optimal measurement. Okay, so then, as I mentioned, we can figure out what the SLD is in matrix form if we have the density matrix, and if we know what the diagonal form of the density matrix is, or rather the eigenstates of the density matrix. Notice that we divide by these probabilities, Pj and Pk, the eigenvalues of the density matrix, which means that if we have 0 eigenvalues, then we have a bit of a problem. And there are other ways of working around that. And so now we have a procedure for optimally estimating a single parameter, because, and this is actually really important, the quantum Kramer-Rao bound, the HCRB, this inequality for a single parameter, can be in fact achieved by something like maximum likelihood estimators. And so this is really good news. It means that we not only have a lower bound for the mean square error for a parameter, but we also have a way to actually achieve it. And so that's all you can really ask for in an estimation procedure, because quantum mechanics puts a limit on how well we can measure things. All right, so that is the single parameter estimation. And even though there are still many open questions there, I think it's fair to say that the basics of single parameter estimation are well understood. But the same is not really true for multi-parameter estimation. Because an evolution may actually imprint multiple parameters on a quantum state at once. And so some examples are, for example, magnetometry, where you may have a magnetic field that points in a particular direction with a particular magnitude. And so you already immediately have 3 independent parameters. Or you may want to do some dead reckoning in navigation, and then you want to keep track of your local rotation, for example, through Sagnac interferometers and the like. And so then you have not only the angle with which you rotate, but also the exact rotation axis. And again, you end up with 3 parameters. Okay, so now we can still apply a lot of the machinery that I just laid out to multi-parameter estimation, and our quantum Fisher information now becomes a matrix. And so for each parameter, now each parameter theta is indexed with an index j. We can define a separate symmetric logarithmic derivative, very much the same as before, in terms of this derivative of the density matrix rho. And then we can define a quantum Fisher information matrix along these lines. And so we rather than having an L squared in our expectation value, we now look at the symmetrized product of 2 symmetric logarithmic derivatives. That's just a technical detail, but it's a fairly straightforward generalization. And so when we do that, we end up with a quantum Kramer-Rao bound that becomes a matrix inequality. So we have our sigma theta is now a covariance matrix, and that's must be greater or equal than the inverse of the quantum Fisher information. Now, this is for a single shot. So I've taken our capital N from before. I've taken that equal to 1, just for to not overly clutter the equations, because there will be more to come. Okay, so then...
Peter,
yes.
You have a few minutes left.
Okay. So I went. Thank you. Yeah. So I will speed up a little bit. So if we want to know what are the optimal unbiased estimators of the parameters, it's not the case that we can just look at the eigenstates of the individual SLDs. We have to actually solve this equation here, and you can see that well, it's a little bit more involved because it involves the product of your inverse quantum Fisher information matrix and the vector of SLD operators. And also, it's not guaranteed that the optimal measurement outcome operators commute. In particular, when the commutator, the expectation value of the commutator, is not equal to 0, then there exists a non-trivial tighter bound called the Holevo-Kramer-Rao bound. All right, so now I have to do a couple of things, and we need to turn this matrix inequality into a scalar inequality. So we introduce a weight matrix. Then we have to construct the second moment matrix of our general operators X. These are going to be some measurement operators that are not necessarily optimal. So they're not the M's I introduced before. And then Holevo derived this particular bound, which is scary. And I just want to point out that if we minimize just over this first part, and this second part is always greater than 0, so we can kind of ignore that. If we do that, then we end up with our quantum Kramer-Rao bound again. But to find the actual bound, what we need to do is optimize over X for both of these terms, the red and the green term. Okay, so now that's a minimization over all possible measurements, which is hard. And so the question is how to do this. Well, it's in our paper, and we have a bunch of algorithms that are really technical, so I'm not going to go through them. But it's essentially, we translate the bound to a minimization problem, and subject to these constraints, which are essentially the fact that we want unbiased estimators and estimators that are local. And so I'm going to skip this slide. For 2 parameters, it's not straightforward, but it's very doable. And what we want is a full rank density matrix rho. And if we find that, then we can, and it is often possible to find an analytic bound. Now, analytic doesn't mean it can fit on one slide. So I'm not going to show that. And I'm going to point you to the paper for details. So what I really want to do, and then for more than 2 parameters, things become much harder, because the algorithms rely on solving quadratic equations, and for cubic equations, we end up with quite a large mess. But we can still come up with fast converging bounds that are tighter than the quantum Kramer-Rao bound. Okay, so for my example, we looked at a proposal by Animas Data's group from Warwick, excuse me, and using these 3-dimensional GZ states for spin to measure magnetic fields. We have to add a little bit of noise in order to create a full rank density matrix. So we add white noise, which is actually, we're going to have that in reality always anyway. So I don't see that as a big problem. And then the spin state evolves to this beast. We have 2 parameters in this case. We chose Bx and By, and those are our thetas. And the state is full rank. The quantum Kramer-Rao bound is not attainable in this case, and the Holevo-Kramer-Rao bound is the tightest non-trivial bound. And then when I compare the 2 bounds, we see this. And so the quantum Kramer-Rao bound is the dashed line, and the solid line is the Holevo-Kramer-Rao bound. And you see that there is a massive difference in the 2. So we really cannot say, oh, well, the quantum Kramer-Rao bound is good enough. And then for higher noise values, so adding more white noise, we see that the quantum Kramer-Rao bound really creeps up to the Holevo Kramer-Rao bound, but still it's not, it doesn't match it. All right, so conclusions. We found some analytic tight bounds on the precision of 2-parameter estimation problems. And we constructed a bunch of algorithms for tightening the quantum Kramer-Rao bound in the case of 3 or more parameters. The algorithms are straightforward to implement, but they're very complicated to explain in a 20-minute talk. Therefore, I hope I have given you enough of a taster to go check out the paper if you want to use these bounds. Because I hope I convinced you that we cannot just ignore the Holevo Kramer-Rao bound just because it is so much harder to find. It really is an important bound. And with that, I would like to thank you very much.
Thank you. Questions?
So thanks, Peter, for the great talk. So I'm just wondering, I was not able maybe to exactly pinpoint the numbers in your plots in the end, but yeah. As we know from the paper by Francesco Albarelli and others, the Holevo Kramer-Rao bound can only be twice tighter compared to standard Kramer-Rao bound, and it seems that in your plots it's better than twice.
Yeah, I'm trying to.
So how come? Maybe there's some square or something additional. I don't know. But in terms of variances, it should be at most twice as good.
Yeah, I'm having difficulty with
my. No, your slides disappeared.
I know. I need to share again. I couldn't flick through my slides. So here we go. Yes, it's that is a good question. That is a good question, and I don't actually know the answer to that right now. So I will have to go back and think about that. Yeah.
Okay.
So
I mean,
it's an important point.
Maybe there is some different cost computed, or I don't know.
Well, like I said, I will have to double check this. Yeah.
Okay, good, thanks.
I suspect that there is a subtlety in the way this is plotted. That makes the comparison not so straightforward.
Maybe we switch to another questions.
Yeah. So so you show here the results when you have noise. So what would happen if you have no noise? Why do you need to assume this noise? I mean, because when you wouldn't have noise, then probably everything would be easier. Yeah, you probably would do analytical calculations. Yeah.
Yeah. So the reason we need noise is because the algorithm requires that. Well, okay. So actually, it's the proofs that the algorithms give us the Holevo Kramer-Rao bound. That require that our density matrix is full rank, right? So it does not mean that if there is no noise that everything breaks down, right? So that's basically not known, at least not to me. So if there is less noise, then the Holevo Kramer-Rao bound will be better, and so will the quantum Kramer-Rao bound. As basically you can see in the different curves here. I don't know. So the question is, well, if I reinterpret your question, is the can you still do create these bounds for let's say pure states? And the answer is most likely yes. It's just that this particular process does not work in that case.
Okay, I think there are no more questions. And so let's thank Peter again. Thank you.
Thank you.